all the Internet of Things topics. I do a lot with IoT Edge and a whole ton with those small form factor GPU accelerated IoT devices from NVIDIA. So cool stuff there. And if you want to follow me on Twitter, I'm at PJ DiCarlo. You'll find some good musings. Usually that's where I post the after hours and the during work hours types of projects that I work on. So to start off with this, the inspiration for this project began on a trip to what is called a Goodwill Outlet. And when I heard that we were opening one of these in Houston, where I live, I could not be more excited. I'm the type of person that when I travel to anywhere for work, the first thing I'll do is pull out the phone and see where's the nearest Goodwill. In fact, when I go to Redmond, I always stay at the Aloft because it is walking distance and I can continue my daily habit of stopping at the Goodwill. I go quite a bit. Now, what's special about these outlets is they're not like the typical thrift shop version that most of us are familiar with, where you would walk in, it just looks like a store. There's items that you could buy that usually are from another time, which is really exciting if you're into old electronics like I am. So this one is a little different format. If you'll see in the picture here, there's these bins, and I've counted, I believe there's like 7 of these per column, if you will. And they literally sound this alarm and call everybody on this intercom every 15 minutes, and they will push an entire column out and roll an entire new column in. And this is every 15 minutes. So you never know what you're going to find. In fact, you can be in the store, and before you're done shopping, there will be 14 new carts of merchandise that you don't know what it could be. Now, I don't know the origins of this stuff, but if I had to guess, it is stuff that didn't sell at other Goodwills because the pricing is way less than you would even get at a normal Goodwill. So here's kind of an example of that. If you're buying 0 to 50 pounds of clothes, it's $2.19 per pound. And my favorite is the electronics, which are at $1.19 per pound. So I was actually in there one day, and these pictures were not taken after the fact. I'm so, I guess, passionate about Goodwill shopping that these are actual pictures from the first time I walked in there. I was just so excited. Now, imagine my excitement as a classic video game collector. I'm walking around in there, and against the back wall, there's all these electronics, and I stumble across this thing, and I had coincidentally been watching these videos on YouTube on like the worst video games ever made, and or hardware, I should say. And the HyperScan had been presented, and it was just so weird that like a week later, I stumble across one of these in that outlet. I'm not sure that this actually cost $2.19. I want to say I walked out of there with something else, but for the title, I did see the receipt. It was $2.19 for whatever I walked out with that day. Now, what happens to be odd, before I even left with this thing, I was already telling my girlfriend on the way out, it sure would be fun to hack something like this, get it to boot Linux or run Hello World or something like that. And I'm going to do it. And I think she kind of ignored me. Then the next day, I was out shopping with my friend, Chris, who we generally go to these flea markets on Sundays, and we were just looking for random video game stuff. And in 2 days, I'd come across 2 HyperScans. So this time in the box with these accessories that I'll explain in a little bit what these actually do. So I took this as a sign. In fact, a lot of the video game projects that I have worked on are often things that I find, and then I'll find more and more and more of it. And I kind of always take that as, this means the universe is telling you to work on this. So even while we were loading this up in the car, I was telling Chris, who doesn't probably know much about technology, I said, I'm Hello World in this thing when I get home. I don't know what that means. Well, neither do I, but we'll figure it out. So let's take this console for this HyperScan, if you will, for a hyperspin. Before we do that, I'll just explain a little bit about it. So it's a system designed by Mattel. It's advertised as a video game system. It's more of a toy that was kind of created to capture the, in the mid 2000s, everybody was collecting like Yu-Gi-Oh! And Pokemon cards and that sort of thing. And this was to sort of capitalize on that, and that you would have these cards that you could buy, and you could sort of scan these in to essentially obtain some sort of features inside of the game. If you want to think about this, it was almost like an early precursor to Skylanders and that sort of thing, except like a decade earlier. And it's actually pretty powerful wherever it lies in terms of, you know, if you were to compare this to, say, a PlayStation, it's somewhere in between a PlayStation 1 and a PlayStation 2. It's about twice as powerful as a PlayStation 1, half as powerful as a PS2. And we'll take it for a quick little spin here. So I've actually got my system connected here. I'll show you what this looks like, as well as the dev devices that I've been using on here. And we'll just go ahead and grab this controller and just show you what this kind of looks like in operation. So it is a CD-based system, so it is going to incur some loading, some painful loading times, in fact. But we'll be able to use that time to talk about the specs, because we haven't really gone into details on that. So this is the pack-in game. I think it's X-Men. We're all familiar with that. And it is a traditional sort of fighting game, if you will. And I'll go ahead and start this one-player tournament mode. And while that's doing that, I'm going to go ahead and get my character card ready. See, you can't just choose from a menu of characters like you normally would with a game. You actually have to find these special cards. And most packs don't have a character card. They usually have a whole bunch of these like modifier cards or whatever. And you hold this over this RFID reader, believe it or not, that's inside here. And hopefully you'll sort of see this. Oh, and by the way, it rarely works. Not because this is broken or anything. It's just the production of this device is not of the greatest quality. But there we go. We got a character in there, and you'll see it's going to mention, you know, scan a mod card. I don't want to bore you with the process of me failing to scan cards again. So we'll go ahead and see if we can jump into one of these battles and see what that looks like. And of course, you'll get a taste of this really long loading time. So while it's doing that, we'll sort of talk a little bit about some of the specs here. So this device, the only thing that I could find about the company that actually produces the system on a chip for this is still on Sunplus, the manufacturer's page, and this was their actual press announcement here. So this was revealed at CES in 2006, and this was just the SPG 290, so the actual system on a chip that's inside this thing was presented there. And it's an interesting company. They have this history of, if you've ever followed Nintendo in Japan, they call it the Famicom, and there's in Asia there's often a lot of what they call Famiclone systems that use these system on a chips that represent a Nintendo. And this company traditionally makes a ton of those. They make multi-carts for those, and then somehow in mid 2000s they introduced the SPG 290 and got into a deal with Mattel to create this device. They're actually a huge manufacturer. There's an interesting article here on HackMe. It mentions that they're the biggest chip company you've never heard of. They're in so many things, it's just ridiculous. And this is a nice little picture here. If you were to go to the Wikipedia, you can sort of see what comprises the internals here. There's that the SPG 290, and you can see here the RFID reader that is used by the games. Now, we should at this point. Yeah, it looks like we've loaded up our game. You can kind of see, it's some basic 3D graphics. I don't think the budget was very high on the production of this particular game, but you can sort of see this is essentially what it looks like. Now, for purposes I'll explain later, I'm going to just go ahead and disconnect my controller, and we'll proceed with the interesting part of this presentation. So that was your introduction to the HyperScan, and as you can see, it kind of sucks. It is not something mind-blowing, but when you look at the specs and you look at some of the conversation, I suppose, that was going on about this at the time, particularly where this was happening was on the Atari Age forums. People thought this was going to be what essentially the Raspberry Pi became before it even existed. So, people were looking at this as being this ultimate potential for emulation because it has this system on a chip. It has, MIPS-based processor that clocked at 108 megahertz and 16 megs of system RAM. So there's, you could emulate Super Nintendo, and that sort of thing on here, probably without too much trouble. That never really came to light, and this presentation will hopefully get into why that probably is. So hello worlding the HyperScan, what it actually involves here. And this is more or less the recipe you would follow for hello worlding any sort of foreign architecture. The first thing is sort of understanding what is the underlying processor architecture and the instruction set so that we can produce code that will ultimately run on that device. Some benefits that we also have from this device, it's not inherently secure. There's no signing of code here, nor is there any encryption that's in use here. So being able to sort of reverse engineer this, there's no imminent hurdles that you necessarily need to cross. And the controller ports themselves are actually communicate over an I2C channel. So it's very possible, without even opening the system, as you'll see when we get into this a little deeper, to be able to communicate directly with the memory simply by connecting up a few wires over the I2C interface and communicating directly with the device. There's just nothing stopping you from that. So assuming that that's kind of the situation that we're dealing with, if we want to actually produce the output of Hello World on the screen, we have to look at creating, number one, a primitive frame buffer, so something that can actually draw data to the screen. And due to the way the SPG290 is created, it doesn't have what's called text mode. So you cannot actually just print text to the screen. It only uses video mode. So in order to do this, we actually have to like compile in a font that we would then draw to the screen as essentially bitmaps after the fact to get some sort of text for the hello world on the screen. Assuming we get all that going, we have to find some sort of a pathway to take this compiled hello world binary targeted to the SPG290 and somehow get that running inside of the HyperScan memory, somehow or another. And at that point, we would then redirect flow to the entry point of that application to start it up, to essentially cause the processor to begin execution at that point in memory that contains that newly compiled hello world program. So the first thing to do here, of course, is look at what the existing research is. And there was probably more of this back in the day. Unfortunately, a lot of the forums have now been defunct. I guess you've probably seen that. You go to an old forum and it says, tap a talk, can't find whatever you're looking for. We've lost so much research from those types of forums back in the day. And that's where probably the majority of this content occurred. And it was spearheaded by someone named that went by the handle PPC ASM. And from what I can glean from LinkedIn, I believe his name is Jonathan Benjamin. And he created essentially the first homebrew style dev kit. And so for the purposes of how we would start to do this, it's not a bad idea to sort of look at what's already out there. There's really two things there. There's a blog post that he wrote, and he had uploaded essentially the majority of the code needed to accomplish this, and we'll talk about what was missing and needed to be accounted for there. So this post, this really short post here, is essentially the entirety of what I was able to come across in terms of reverse engineering the HyperScan in a short form. There's some paragraphs out there that contain some little nuggets, but this is essentially what I relied on. And what was really important was looking at these pinouts for the controller and realizing, very quickly, seeing those data and clocks that, yeah, this is an I2C interface. This is something you can probably communicate with a microcontroller. If we jump over to the GitHub repository for this, it looks like 7 years ago, this code was dropped into GitHub, and for all I can tell, it was essentially forgotten about. The way this works, I'll sort of walk through it without reading necessarily the README out to you, but there are three pieces to this. There is PC side code that will take a properly compiled binary and send it 1 byte at a time down to the MCU or microcontroller side, which in our case will be this Arduino. And that's going to communicate with a program that is running on the actual HyperScan itself that will be listening for I/O on the controller port channel over I2C, and it will pull out the bits that are coming through there. And so you will have to build 3 separate projects essentially to get this up and running. And of course, the other really important piece here is noting that the male controller pinout, which corresponds to, sorry, wrong screen, which would correspond to this area here, that sort of designates how you would connect an I2C interface to this. So this is fun. You know, when I saw this, I was like, oh, cool. You know, surely I'll be done with this project in an hour. I'll just basically copy this guy's tut and we'll be done. That wasn't necessarily the case. The very first issue was, excuse me, I noticed your make file is looking at a tool chain with the following name. Where do I obtain this tool chain? And so I'm looking around. I was looking around at builds of GCC at the time, the GNU C compiler, and looking to see if it had support for this platform, which goes by the name SCore for Suncore. And you'll notice here, this was back in, this is an older post that mentions, you know, SCore support has been removed from upstream GCC. Okay, well, that looks promising. It looks like this happened in 2018. That's not the case at all. It was actually removed quite a bit longer. From what I can tell, I believe it was removed around October 3rd, 2014. They totally just took this out of the GCC mainline. And what's interesting to note about this, if you wanted to easily install like a prior version of GCC that maybe had this version in it, that's fine. All you need to do is go get GCC 4.91 or less, and you're off to the races. What's really funny about this, if you were to pull up, you know, stock Ubuntu and, you know, look at the available package versions for GCC, it stops at 4.9.2. That is in the public repositories anyway. The furthest back version is 4.9.2, which was released on October 30th, 2014. And you'll see this just missed that cutoff. So my life could have been easier, I should say, in that maybe I could have obtained this tool chain just in an older version of GCC. That's not really the case. You'd either have to compile this in yourself or compile an old version of GCC from source, which just is not fun. Now, the other option was that Suncore had released an IDE, and thankfully PPC ASM, I actually kind of nudged him in an email chat to get him to upload this here, was able to throw that over the fence. And so what you'll see as I kind of proceed here is going to take place inside of this IDE that was released by Suncore, that thankfully he had like on a jump drive or something, somewhere in his archives, because otherwise this is as far as I can tell not obtainable on the internet publicly right now. I mean, maybe if you wrote a nice letter to Sunplus, they might send it to you, but I did end up obtaining just a previous copy of this, and this code just did not just work out the gates. I'm gonna just check here, make sure we're not missing any messages. Okay, awesome. One of the quick things that I noticed it was doing was changing the start address of the code that it was producing, and so we had to fix that. And you can dig into that deeper if you'd like. So let's talk about this game plan here. So having gone through this previous research, how do you actually turn this into something that would present Hello World on the system? Well, step number 1 is we burn the HyperScan side loader to a CDR and boot that. Once we have that booted up, we can then wire up the Arduino device to the system, and hopefully be able to just, you know, send some data back and forth there to verify it's actually reaching the other side. And then finally, we need to actually create that Hello World program and send it through a PC side loader that will talk to the Arduino. And so if you kind of go back to the picture here of this live setup, what's going on here. I've got the device here, and that's going into the system itself. And this device is actually going to need to be plugged into my PC. So I'll go ahead and sort of change this out right now. Get this plugged in. And let's pop this disk out, because we're going to need to examine this. I want to sort of show how we would reverse engineer essentially one of these games, given that we look at its file structure in, say, a hex editor or something like that. That's going to be important. So moving the real game into a CD reader, and we'll come back to that in just a moment. All right. So burning the bootable CDR. It's relatively straightforward. I should really put that in air quotes. You will start by looking at a real game. And if you were to launch one of these, you know, say you're looking at this in Explorer or whatever, something sticks out as probably being the entry point here, this file hyper.exe. It's probably it, and it is. And if you were to open that up, you'll see in the hex editor, and I do apologize, I can try to zoom in on this if anyone needs. You'll see this top section and a whole bunch of zeros that sort of continue on here, this address OXC04. And this is really something, just having looked at these quite a few times, you know, various different game systems do this, even the Famicom disk system. This looks a lot to me like a special header. Now, I don't know what this header is necessarily doing, but it seems like this is required to be there. And the guess there is that the firmware, before it would load this hyper.exe, is actually going to verify that this exists before it attempts to load the code that follows after that end address. Now, this is not something that you can necessarily decompile. In fact, we know that this is not in what would be called executable linkable format, because there's no mention of that here in the opening section of the data. Just to give you a quick example of what I mean by that, an ELF file will typically contain something that says like .elf right at the very beginning of the file. So what we need to do is somehow take this exe and convert it to an ELF. And the reason why we wanted to do that, if we convert it to an ELF, we can disassemble this and start to look at what the actual instructions are doing in this header, assuming they even are, because sometimes they're not even real code. Sometimes it could be encrypted code. Who knows? But that's not the case here. So the way that we do this, once you install the S Plus Core IDE, it's actually going to bring along with it, within this directory GNU/bin, a compiled version of GCC and all its associated tools, except these are targeted for operating on the S-Core platform. So meaning the instruction set that this game console uses, this version of GCC knows how to compile for that target. It also knows how to disassemble it. Now, the trick here that you would do to go ahead and get started with this, there's two programs, obj-copy and obj-dump, that become important here. So the first one I've done here is running obj-copy. And what this will allow me to do is convert a .exe file to an ELF file given specified parameters here. So what I'm doing, I'm invoking the object copy program. I'm saying the input target is raw binary. It is not in ELF format. It is raw binary. Treat it as such. And we want you to output this as ELF32 little score, which means ELF 32-bit format in little endian format that targets the S-Core architecture. And when I say little endian, that is in contrast with big endian. It depends on whether the bytes flow from left to right or right to left, and vice versa. And finally, telling it what that binary architecture is. So saying this is S-Core 7, and I want you to use the hyper.exe input. So this is me copying hyperexe from the actual game to my desktop, and I want you to output that as hyper.elf. And once we've done that, that's going to spit out essentially what looks like the same file, although now it has the ELF header on it, and it's also going to append a bit of metadata down at the bottom of this file. And this is important because all ELF files will contain this, and it makes it accessible for disassembly. So I'm going to now run the next command here. We're going to use objdump on this newly converted ELF file. We're going to use the -d parameter, and that's actually going to spit out all of the assembly for this using as though it would look with S-core mnemonics. So this is that instruction set architecture. Notice there's a whole bunch spitting out there. I'll show you what this looks like real quick in a text file, so it's a little bit easier to follow here. So if you look at that first section in the hex editor, I'm sorry, I had the wrong things up. And we look at these side by side. So look at the header here, and then you look at the actual assembly output here. You'll notice this is a series of jumps that are essentially jumping into the program itself. I don't know why this is. If I had to guess, the firmware probably skips up to OXE04. So where all these zeros are, the firmware is probably saying that when you see this hyper.exe, skip all the way to OXE04 and resume execution at that point. There's also some interesting commands down here. And if you're able to get a hold of an ISA book that'll explain to you what these do, they're actually initializing the hardware on the system. So when you turn on the HyperScan, it has some portions of the hardware activated. As you leave it on and it executes the sequence, that probably does things like, activate the RFID reader and those sorts of things. And this goes down for a little while. Now this is important because if we're going to assemble a Hello World program, or I should say in this case, a program that can be read off of a CD and booted by the HyperScan, it's going to have to look exactly like this format. So we need to assemble a binary that has sections that look exactly like this all the way up to OXE04. Then we produce our binary would follow right after that and needs to be targeted to the S-Core 7 platform. Well, the IDE certainly helps with that process. It doesn't solve it for you completely, but it certainly helps. And so if you look here inside of the CD application, we'll kind of jump into the make file here because this sort of is where you would start understanding how this binary actually gets built. If you've ever cross-compiled like on an x64 platform for, say, ARM, you've probably seen this before where you have a cross-compiler flag. You'll notice a lot of references to that, and that's calling into that S-Core ELF GCC file. So remember, that's part of the tool chain that's included in the IDE. And it's throwing a few flags over here, telling it to use the S-Core 7 architecture. This is mentioning that it wants it to use little endian format. And down here, you can see where it's actually assembling that binary. So it produces the startup.o object, which then gets linked to main.out or main.o, I'm sorry, which at the very end contains libgloss, which is essentially our common functions that we're going to use for things like reading and writing and stuff like that. So this has to be set up like this. So this these object files have to be built in this order, and they'll start with the startup, then they'll add the main, then they'll add libgloss. And this is all verifiable if you were to use those, the object dump tools and stuff like that. So let's look at the first thing that gets built here, the startup.s. And you'll notice the first thing that we do to essentially recreate that header is we start at address 0, and we start using the hex format of what is actually in that header payload. And we write that all the way down to here where we skip over to offset OXE04. That is where it ended previously. So this makes a little more sense. If you look at these two things side by side, there's your 0, 0, your 8, 3, your 12, 8, 8. And you'll see that we jump all the way over here to OXE04, which causes this to get filled with nothing but zeros. Then when we get down here to the hardware init phase in the raw assembly, this is actually snipped out of that output that was RE'd earlier when we ran this through object dump. So you'll see here the number of calls that get, or these assembly instructions that get called here are going to match up to things here. So you'll see the MFCR R5 CR4 followed by a no-op, followed by R7 OX70, etc. So we sort of patch this all back in, and this gives us what to the HyperScan system is going to look like a valid header. And provided that there is a binary at that offset OXE04, it will execute that. That's really all there is to that. I know that can be quite daunting if you've not seen that, but that essentially helps us set up the initial portion of our loader. One other thing to sort of look at here, just to look into main.c, how this is working before we set up our MCU code. You'll see here that this actually listens for 4 bytes. And this is going to make sense once I bring up the Arduino code in just a moment. Those first 4 bytes are the upload address. The next 4 bytes are the size of the payload that's coming through. And what we do then is we calculate a checksum. And provided that that checksum matches, then we go ahead and jump into the entry point. Now, this is interesting stuff here if you want to look at how this works. The upload address that first comes in is assigned to a void pointer, and the actual hex representation of the binary that's going to come through gets assigned to a char pointer called points. By assigning this particular address to a void function, this looks like a typical function to the program running in C, and provided that we upload this binary into executable address space, if we jump to that newly defined function entry point, that will begin execution of the binary formatted code that has come through our microcontroller into the console. So hopefully that makes some sense there. So now the next piece, adapting the solution to a modern Arduino. So looking at PPC ASM's original code, he was actually targeting the Arduino Mega, which is I guess an older form of an Arduino. I've never owned one. It was maybe one of the first models. Someone could probably correct me on that. But I didn't have one, and I thought to myself, well, surely all Arduinos are the same. I'll just, take your code and just flash it over to mine, and it should work. And that is not the case at all. There's some subtle issues here that are pretty interesting to point out. So here's the original Arduino Mega pinout. There's nothing super special there. All we need to do is set up an I2C communication over the clock and data lines. We do not need to provide power because the controller port is self-powered from the HyperScan itself. And also these enable and reset lines we don't really need. The enable line tells you whether that is one of the currently read channels by the system. And it actually flips back and forth. The HyperScan is constantly looking at port 1, port 2, port 1, port 2. So in order for you to accurately send data, it's important to note you don't want to have a controller plugged into port 1, because if you do, the enable flag might switch over to that and it might read data from there. Then what we do, we essentially come down here into a send byte. We take all the bytes that are coming through a serial program, and that is read. It's read out bit by bit, I should say. So each byte is pulled out, and then we shift that over 1 bit at a time and send that over over one of the active outputs using just simple digital write. Now, what this is a textbook implementation of what's called bit banging. So I'll show just a quick little demonstration of what that is and why this is the textbook example of it. If you look this up on Wikipedia, there's a nice C code example, and essentially all bit banging is a software version of performing serial output over a device. So what you do, you look at each bit. If the bit is high, you output high on the digital output. If it's low, then you output low. And there's no real clock that's necessarily needed for this. As long as you're sending those bytes over at the appropriate speed, they're going to write out at approximately the same speed. Now this causes some odd issues and is potentially the reason why I experienced some timing issues that we'll talk about. But as you can sort of see here, if you compare these two blocks here, this is essentially what that is. It is textbook bit banging going through the MCU side. So a few things to note here. You can take this code, ship it off. It doesn't really matter what ports you use, except you do not want to use the hardware serial pins. If you've ever used one of these Arduinos before, you probably are aware pins 0 and 1 are dedicated hardware serial lines. You do not want to do that because there's a clock signal in there that will essentially send unwanted data across. We are purely re-implementing what looks like serial transmission over the digital write off of those pins that have been designated as digital outputs. That's really all that's going on there. Now, when I talk about timing issues due to bus speeds, there's a variety of weird things that go on here. If you've ever dealt with legacy machines and tried to communicate over like COM ports and things like that, sometimes the slowness of older machines is actually a benefit to you because the cycle speeds when it does transmission of data is way more accurate. When we look at more modern types of buses, like your USB 3s and things like that, sometimes they'll do things like maybe in the initial communication that are so fast that it actually causes errors across your data line. Usually these things can be ignored, but it does seem like this potentially surfaced in this next segment. So I can't reproduce this on this machine that I'm demoing on now, but if you'll take my word for this, after I built the PC side loader portion of this, which I guess we can explain for a moment before I jump in there. The PC side loader was a dev C++ project. If you've not used this, this was something I had used since I was in college. But I saw that .dev extension, got excited, pulled down this old school IDE and took a look at the code. There's not much going on here. It essentially sets up serial communication over a COM port, takes file input, and just like what we saw the MCU doing, it breaks that out a byte at a time and sends over those bits, sends those over actual serial to the MCU. So it sends those over legit serial to the device. So that's all that's going on there. So imagine that I've compiled that already, and I'm testing this over, using speeds like 9600. And I'm noticing that the output that I'm getting there is always prepended with data that was never in the file payload. It was always prepending F0. And this was a weird one. I mean, I went to bed on this just thinking like, is this a timing issue? Is this something wrong with the way I wired this up? I always get my data, but it's prepended with F0, just for whatever reason. I'd see a whole bunch of ones and a whole bunch of zeros, which signals that could be a pulse, so like a rising edge and a falling edge. So I just got lucky somehow with a Google search, or binging with Google, I should say, and came across this post on the Arduino forums that mentions, that essentially mentions here, someone that's facing the same issue. They call it the F0 problem, and it's actually described in a bit more details here on the Italian forum. So you actually have to, believe it or not, you have to translate this to understand the problem. But what they were saying happens is the Arduino itself has a bug in the firmware, in that at speeds over 9600 baud, the AAB Mega 328P, which is the larger chip. So if I bring up my my screen here, if you look at the Arduino, the larger chip here, this would be the 328P. That's essentially the 8-bit. It's the brains of this device. When you initiate a serial connection to the device, this other coprocessor down here, which you can sort of see I'm pointing at, it's located about right here, sends a pulse over to the 328P. So this thing, the AAB Mega 16U2, sends a pulse, and that ends up getting read as F0 in your serial data transmission. I tried to get wise about this and see if I could like maybe trap that, and it just never worked for whatever reason. And also, I gotta hand it to PPC ASM for this, because as we showed when I was looking at the code earlier, he'd implemented CRC checks, so checksumming the data that's being sent over, which is really smart because it wasn't until through trial and error that I dialed this down all the way to 2400 baud that I could not only send this data, but also get the checksum to validate. So now that we've kind of explained all of these pieces, we'll talk about the last piece and we'll do it. We'll actually execute Hello World on this device. So the first thing we need to do is create this Hello World program. Now, in order to do that, it has a bit different rules. It cannot have the executable header because, as you saw in our disassembly, that causes it to jump back to itself, which will kind of put you in an infinite loop where you're never executing the code that you want to. So I've gone ahead and created a second program that sort of looks very similar to the original one we were looking at, except in the startup portion, you'll notice I don't have the header there. I immediately jump into start, and I make sure to jump in at the same executable address in memory, this OXA1000, and just wrote a basic Hello World program with of course, PPC ASM's primitive frame buffer behind this. We build that program. We end up with essentially a binary format that we can then send over through the PC side loader. And so that's what you see here. So this is the PC side loader, essentially getting ready to execute that output. The next thing we need to do is load up, of course, our newly modified HyperScan side code. So I've already burned that to CDR. We'll go ahead and launch this sucker up. Make sure everything's wired up. Turn on our power, and let's see what we get here. Here you can see the system waking up, and hopefully we get some video output here. And so this shouldn't take too long, and hopefully we'll get this on the first try. So you'll see there's our HyperScan side code uploader has now launched. And what I'll do over here on the side is begin the transmission of our PC side loader that's going to throw over that Hello World binary and start shipping that over. And hopefully we'll get a good result here. So see there it is sending at 2400 baud. You can see that the program picks up that it is sending to start at A1000, the start address we looked at earlier. It gets the size accurately, 1E80. And as long as that CRC check matches, we should be able to jump into that entry point, begin execution at the Hello World program, and get Hello World output onto the screen. So there we go. Everything has been loaded. And there we go. That is literally what I wanted at the moment that I bought this thing from Goodwill, finally appearing. And so as you can see, there's a lot of work for this glorious result. And that is actually a picture of the moment. I want to say this was 2 a.m. on a Saturday. Who knows how long I'd been working on it that day, but it was really exciting to sort of see this on the screen because the dev kit never really shipped with code on how to put it together, and just by some kind of trial and error, understanding, looking at those GCC tools, looking at the doing the disassembly and all that, really pointed all the clues that essentially made this inevitably possible. So what do you do after you do this? Well, at this point, we now have essentially a dev kit set up that we could, port really any arbitrary portable C code to and get it to run on the device. So one of the popular things people will do, they'll usually start off with Unreal or Doom, because Doom is 100% open source. It's id Software's popular shooter from the 90s is open source and available on GitHub, and it is written fully in C. It's totally portable. In fact, if you head to the subreddit for It Runs Doom, you'll find a variety of different devices, including ATMs, various different leapfrog toys that children will play with and things like that, all running Doom. And the way they do this typically is they use SDL Doom, which is a simple direct media layer, which allows you to have the primitives for, say, audio output, controller inputs, video output. And so as long as you're able to port SDL to, say, the SPG 290, you could pull off, you know, SDL Doom, rip out those, or put in, should I say, the appropriate SDL layer, and you now would have Doom essentially running on the device. And this idea has actually been talked about as recently as 6 years ago on the Doom World forums. There's actually a post about this. So it's a HyperScan port possible? Yeah, totally. It's totally possible. And, you know, just some folks talking about this, actually as recently as 5 years ago. That has not come to be. It is something I did spend a half of a Saturday on. It's certainly possible, but that progress has not necessarily been made at this point. The second thing that'll be interesting to do is running Linux. So the recipe for this essentially starts with having a bootloader to be able to boot up your Linux image. The popular way of doing that for the longest time is using DOS U-boot. So you would port this to, say, SPG 290, and then take something like microcontroller Linux, port that to SPG 290, and you would somehow use this this dev kit essentially to launch U-boot and then have somewhere in memory the image of the SPG 290, and you would effectively be able to boot Linux on this device. That was so close to happening. In fact, I was looking here in the GNU task list here, and you can see there was at some point in 2007 a request for porting microcontroller Linux specifically to this platform, the Sunplus S Plus core. They even call out the SPG 290. You can do it. You would just need this compiler, and you would need the source from that time period, and you could build that image. And I did find one offshoot forum where it does seem like someone had done this. So someone here had actually built that image and targeted it to the SPG 290. And that is effectively, if there's anything that you've learned from this, you know, if you're ever wondering how people are getting Doom and Linux to run on things that, you know, you wouldn't think it should, it just comes down, compile it for the architecture, make sure you have, you know, your primitives set up, easier said than done, and have, of course, a bootloader to launch that off for you. Now, you might be thinking, what was the point of talking about a decades-old video game console? Does this have any relation to, you know, getting code execution on, say, modern systems? And I would say yes, absolutely. If you look at the Nintendo Switch, early versions that came out had a vulnerability in the Tegra system on a chip, which features a couple quad-core ARM-based processors, so the Cortex-A57 and the Cortex-A53. And the way that this was done, believe it or not, the bootloader on the Nintendo Switch is subject to a buffer overflow exploit. So the way that you get access to that, people have made these dongles, and also if you want to MacGyver it, you can actually bend a paper clip. And if you short out the two pins on the right Joy-Con port, the two furthest pins, it will cause your system to boot up in what's called RCM mode, or recovery mode. Once you're in that recovery mode, you can, if you think about this, I mean, it's almost the same thing. Instead of connecting to an Arduino, you connect the USB-C port out to a device, and you send a specially crafted payload that will overwrite what the stock bootloader intends to launch. So what they typically started with was, believe it or not, a port of DOS U-boot. And of course, all you have to do at that point is grab current Linux source, compile it to target down to the Cortex-A57, and you will essentially have a pathway on a modern game console. And of course, this only works because this exploit exists. If that did not exist, this would not be as easy, nor would this mechanism look like this essentially. But that has opened the door on a modern platform for plenty of homebrew, including things like Doom, Linux, and RetroArch, if you're into you know, system emulation for other game consoles. So with that said, I'll go ahead and open it up for questions and answers. So feel free to come off mute. We've got about 8 minutes, but we can go over. We'll go until Stacy says no more.
Hey, this is Brian. I got a quick question for you. Did you have a look at any of the games that came with the HyperScan, and maybe run them through like a tool like BinWalk or something like that to see if you could like disassemble what their stock images are on those disks and see if there's like stuff you can glean that way?
I did try pushing this through Ghidra, and I had a feeling even when I did it, there's no way this thing supports the Suncore mnemonics, and it doesn't. You could. There was a former version of BinUtils at the time when this processor was on the market that you could probably use for exactly that purpose. But I would just the fact that this isn't in mainline GCC, it isn't in mainline Linux. The odds that someone would be carrying that around, even in something like BinWalk, I would say are extremely low. Could be wrong though, but I'd say it's extremely low that they'd have support for the S-Core mnemonics there, or mnemonics.
Hey Paul, this is Adina. This is a great talk.
Hey Adina.
Was there any part of this where you felt like you came really close to being blocked? And if that wasn't the case, what part of this would have been like, if you hadn't had figured it out, would be like, well, I guess it's impossible to do because the architecture is too old?
There were two main things. The number one was getting the tool chain in the first place, but not just getting the tool chain, understanding what are the intricacies of the linker script involved to build something that will actually properly execute on that device. Thankfully, I would say PPC ASM had solved most of that up front, even though there was some cleanup that I needed to do to actually get that to work. So that would have probably been a blocker in a world where his research didn't exist. The second one was the loading of the binary and realizing that you had to trim the header out because it had those assembly instructions that would cause you to go into an infinite loop. That I had a hunch about, and I would have gone down the path anyways. That was a for sure, but I felt really good about it because I emailed PPC ASM and I asked them point blank. I said, I have a feeling that this header has to be removed in order for this to work. And that's when I got the answer. Yeah, you're totally right. It does. So it was close. It was really close to throwing it all away. But thankfully, that didn't happen.
Thank you.
Hey, Paul. Great presentation. Really enjoyed it. First of all, shout out to HXD. Real ones know. So glad you're using HXD. Also, I'm curious to know whether you think, obviously the first thing my mind went to once I saw the Arduino communicating over the controller port was like, so we need to get some internet happening, internet connectivity. Think it's possible?
Yeah, we can do anything we want at this point. We have a 2400 baud direct line to the memory of the device. So yes, it's totally possible. Unfortunately, it's at 2400 baud, but yes, you could essentially load anything you wanted at that point.
Well, you'd have to have a pretty good, since it has to come in, like you said, you're having to sort of write the image like a pixel at a time, right? So you'd have to have some pretty intense pre-processing before you could do that. Does that sound right?
Yeah, there's a bunch of delays in the, you'll see it in the PC side code where there's delays to actually wait for the screen to draw because, yeah, so even though you have this this thing that goes at 100 some odd megahertz, yeah, we're not going to be, we would not see that type of performance unless you loaded like a full binary in and let it rip on the processor, yes. But as long as we're communicating to it from the outside world, unfortunately, no.
I might have missed this, is Brian. Did your serial link that you've got kind of going there, so you got the PC to the Arduino to the HyperScan. Is that bidirectional? Like, are you able to get data back from the HyperScan?
No, this is unidirectional. You could, though, write a program that runs on the HyperScan side to dump data back out through that port in almost essentially the same way. You could do that, but that is not implemented right now. An easier way to do this would be to maybe instead write some instructions that would dump like the state of the registers or something like that to the screen. Would be a possible way to do something like that, where you could essentially get data of what's running on the device while communicating with something like this. I don't know how you would do that in, say, like a multi-threaded approach for this architecture, because you'd probably want that. But that's kind of the approach you'd have to take, or I would suggest is like, just dump the register output to the screen and go from there.
So this is David. Got a question. Did you look at possibly hacking through like the RFID interface? It's going to be communicating something, maybe that's a little more performant than going through the controller ports.
Oh, that's interesting. No, I didn't think about that. Like whether you could maybe perform code execution via scanning of a card. What's really interesting, these cards actually have memory to them too. So, I mean, they're RFID, so they don't just read, they write as well. I guess that would depend on whether there's some sort of a pathway on that data bus from the RFID, into direct memory that we would probably still need a program running on the HyperScan side to direct execution to those address lines or whatever memory that those lines might have access to. But that would be really cool. And it reminds me, your question also reminds me in the Doom forum, they were suggesting it would be really cool to have power-ups that you could like scan a card, and like you get more ammo or something like that. So, lots of ideas for fun things like that through the obviously it's feature that would draw people to it, the scanning, right? Hence HyperScan.
And then on the HyperScan's main board, is there no like JTAG interface that's maybe hiding somewhere that maybe?
There is. There certainly is. In fact, I believe that there is. It's off one of the headers. There is what looks like a JTAG port. I didn't open any of these systems, believe it or not, in order to achieve this. But there is supposedly accessibility through JTAG, and there may also be an SPI line that you can attach to just going off the specs of the processor.
Yeah, it looks like it, because if you put a couple small leads off that processor, probably based on it, we could even sideload the whole thing directly to the chip.
Oh yeah, it gets super fast.
It's nice that it goes through the controller port, because then you don't need to open anything. And you could theoretically do this as a nice party trick. You put your Arduino and you put your little chip in there, and you have it in a nice 3D printed case, and just kind of, not that this thing ever exists, but it'd be kind of cool. Pop in your CD, pop in your controller, and all of a sudden magically you've taken over, their device.
Yes, I love that. That's well. And the other benefit too is the uninhibited speed, of course.
What's that USB port on the back there? Is that at the bottom there? Is that just data, or is it power?
It's not used, although it is theorized in the firmware. It is theorized that you can actually mount data from here if you can somehow boot it into a recovery mode that no one has yet divulged or discovered. But the firmware dumps do indicate that you can mount data from that USB port.
Huh.
Just the question is how. No one knows. It's probably a recovery mode. Unknown how you would get into it.
It's probably in that whole first section of the memory headers that you wipe over with zeros. Probably set a couple flags in there to actually boot up, and that loads like a like a pre-environment that only the SDK developers would have known.
That's the guess. Yeah. It'd be interesting to see that come to light, because who knows, maybe it's a button combination. Hopefully there's some way, you know, where you don't have to destroy the console to get to it, but that would be really cool. And then you could, of course, you know, have your payloads loaded through a USB, and it'd be real easy to transmit data, you know, try experiments and things like that. So definitely onto something. If someone was to really pursue this and go like the Doom or Linux route, you'd probably want to get that activated first.
I'll make sure to add that to my to-do list as, you know, project number 455,212.
Hey, that is okay. I've got two. So the first one only cost me $2. So if it ever comes up on the queue, let me know. I'll send one to you.
Quick question. How did you get the video output from the HyperScan onto a window on your desktop? Yeah.
So I bought this $10 dongle from Amazon. I'd have to look it up. And you know, sometimes you try something, you don't even know if it'll work. I'm like, you know, before I install their proprietary driver, let's just go into VLC. That looks like something that could work. Open default, open device. Okay. And then I clicked through here and I was like, I haven't seen that before. AV to USB. The screen was all messed up, but then I saw I could type in the video size. I put 640, 480, and it came out looking like this.
Fantastic.
First try. I'm not even kidding you. There was no Googling. I just opened VLC and looked at the freaking thing and was like, well, that worked. Can't believe it.
Yeah, that's actually a really good find, honestly.
Yeah, it really is.
It feels like there's some delay here, though, because, like, believe me, I'm so tempted to, like, especially in this age of live streaming that we're in now. I play so many games at night, and a lot of my stuff I do play through component or composite, I should say. And it's good. There does seem to be some sort of a delay here, though. Like it's definitely not live. But yeah, if you're wanting to stream, you know, your old NES or your Super Nintendo or whatever, yeah, it's a $10 dongle. I think I just looked for composite to USB on Amazon, and there you go.
Hey, Paul, have you tried seeing if it'll show up as a source in OBS?
I have not. I have a feeling it would. The fact that it shows up as a direct show device in VLC, I have a strong inkling it would work. And if not, you could do the old.
VLC might have added some of that delay.
But in the case that it doesn't, you know, you could always, you know, do the old, you know, snip out this region of the screen and get this over OBS if you needed.
So that IDE that you got, did it come with platform libraries?
Oh, it comes with something that
I'm just wondering if it's got libraries to talk to, like the USB and the RFID and all those things.
Yeah, and I didn't dig into these. You'll see there is an SDL.dll, SDLnet, and SOC.dll. So totally, yes, these are probably those things. I just hadn't dug into these to see what exactly is available in them. But that might even be the trick to how you get this. You know, again, I think porting Doom might be easier than I think it is. Just looking at the fact that it is packaged with SDL, assuming those are legit compiled 4S core, which they should be, these might get you most of the way there. I mean, the retail games are drawing to the screen somehow. They're using something, and I would wager money that it is these SDL libraries here.
Have you tried using the wire library in the Arduino to get the hardware I2C?
No, I haven't. There is some belief that would totally work, and again would probably give us more stable transmission as well as faster transmission. There is something cool though, I will say, about implementing bit banging and really seeing it live that I thought was really cool.
Right.
You know?
Right. Yeah.
Even though it sucks in terms of speed and accuracy, it's cool. It's just so cool. Like, and you know, without changing code, you could bit bang this to other devices. You know. So.
I think probably, especially when it came down to your Arduino experience, where you were running into the baud rate issues and the likes, that the Arduino Uno may have actually been more of a problem for you than than it needed to have been. Because I mean, literally, when you look at it, you've got 2 Arduinos on that one board. They're using the Mega chip to do the USB serial interface, and then they've got the second Mega chip, which is the actual Arduino itself. But going with more of an old school Arduino, and that would be like the Mega, which would have been an Arduino with almost like a built-in FTDI chip to do a USB to serial. That might have not caused your baud rate issue where you get that FZero stuff. And then you could have also theoretically gone, I mean, almost straight PC based as well. Just using an FTDI adapter with the FTDI SDKs and actually go serial without using any of the additional DTS lines or anything like that.
I wonder if we did that. That's a great point. I wonder if you did go straight FTDI, if you would still have to go as slow though. Like I'm not sure what is causing that bottleneck. I almost feel like it's actually the HyperScan that's causing that, but unknown. Well, no, it can't be, because with the Mega you can get speeds of 115,200. So yeah, that's actually a really good idea. And then just throw the MCU out and just go full FTDI. I love it.
Do we know if the sock is directly connected to those game ports, or are they running through some sort of I/O wedge chip?
From what I understand, they are direct. They are speaking directly to it, which is partially why we get direct access to the available memory on the sock as well through the port.
I was thinking it might not be a bad idea to just try a dump in on those SDL DLLs and see what it lists. It could give you a whole bunch of entry points that would be interesting for knowing if those are actually going to be a valid way of trying to draw.
I'd love to see it too, because again, I think this is basically what's standing between Doom running on this device is, SDL Doom and a proper version of SDL. Just link them appropriately. It should work.
If those SDL letters stand for the SDL we all think it is, you could be really close to having Doom.
If anyone wants to do Doom on this, because this might be a consorted effort here, please ping me. I probably need help. I did attempt this one afternoon. I'm not going to say I hit a stopping point. It's just like new projects popped up. But if someone really wants to do this, I'd be happy to work with someone in the after hours on this. So please, hit me up on Twitter, Teams, whatever. Especially if you've done an SDL port before, that would be super ideal. Like,
any other questions?
Stacy, can we publish?
We can
this?
like unmute our mics and yeah, we'll publish it. I can give you the link. And we'll put it up in a place where everyone can see. Maybe everyone can unmute your mic and you can clap for Paul. That would be nice, maybe. No? Thanks, Paul. Your talks are always so passionate. I love that. Half the stuff you're doing is over my head, and I still coming away with so much. So thank you so much. Thanks everyone for joining. And we'll make sure that we put any of the resources up, and we'll put this call up as well in the stream. Thanks, Paul.
Cool. Thank you everyone for tuning in. A lot of familiar faces and friends. Thank you all. And thanks for having me, Stacy.
Yeah, always. All right, everybody. Have a great day.
Bye, everyone.